So this is obviously a R theta problem. There's the sliding rod and the collars on it. And it's kind of interesting because the collar is sliding on the rod but also sliding along this circle. A few comments before we start. The problem, the word problem said, both collars are 0.5 kilograms. I read that to mean both collars are 0.5 kilograms each. But I just looked at the solution, and the way they worked it out was both collars total to 0.5 kilograms. So, no, not each. It's the two of them are 0.5 kilograms. The other thing is that it does say that this is in the horizontal plane, so we don't have to put the weight in. The previous problem I did, I missed that it said it was vertical, and so I had to put the weight in. And so that will simplify this. We will not have weight in the problem, just radial and theta. Okay, so let's get started. So I'm going to try and draw the free body diagram of this collar. And what you have to imagine is that loop is catching the collar but cutting through those rods. I'm just going to draw that whole mechanism as a giant dot because I don't want to draw it. And they're all particles. Okay, and so I'm going to dot in the rod there. And I'm going to dot in the circle. Okay, this looks like the geometry might be a little painful. We'll see. There's theta. And so the free body diagram is that, I've accidentally drawn my circle perpendicular to the rod, which is not necessarily the case. I'm going to redraw that. I'm going to exaggerate it so it's less confusing. So I'm going to say, here's the part of the circle we're looking at, something like that. Okay, so there are two forces on the pair of the collars. There's this force that's perpendicular to the rod, and I'm going to call that F rod. And it says frictionless, everything's smooth, so that's why it's perpendicular. And then there's going to be a force perpendicular to the circle, and I can see that this is going to be a nightmare in geometry. We'll see. And I'm going to call that F circle. Okay. So those are the two forces. There's no weight. There's actually weight going down into the paper and a normal force coming up out of the paper, but we don't have to worry about it. And as usual, that all equals to the mass times acceleration diagram. And so it means that we have M a radial, and we have M a transverse of theta. Now these are at right angles because they're R and theta. If you look at the picture carefully, the green circle is not perpendicular to the brown rod, but this is all in terms of the brown rod. So the radial is along the brown rod, and the theta is perpendicular to the round rod. And this geometry of trying to figure out the angle of the circle relative to the rod, I'm not looking forward to that, but we'll see how it turns out in the end. Okay, so to do these sorts of problems, we have to know r dot, theta dot, and all those sorts of things. So let's look at what we've got. We've been given that theta dot is 4 radians per second constant, which is nice because that means theta double dot is 0. And we're given that r equals 1.6 cosine theta. And so let's just go right ahead and do r dot and r double dot. So I've done this enough now where r dot equals 1.6. The derivative of cosine is minus sine. And then by the chain rule, theta dot. That's nice. And our double dot equals minus 1.6 times derivative of sine is cos theta, and by the chain rule another theta dot times theta dot plus sine theta times theta double dot, which is 0. Okay, so I'm actually going to just put in theta dot and theta double dot. So that's minus 1.6 sine theta times 4, and that equals 6.4 sine theta. Our double dot equals, that one's going to be 0 because theta double dot 0, minus 1.6 cos theta dot squared, and theta dot was 4, so 16 times 1.6 is 25.6. Okay, so that's pretty straightforward. They want to know all of this when theta is 45. So when theta is 45, sine theta is 1 over root 2, and cos theta is 1 over root 2. So finally, we have, let's see, theta dot is 4 radians per second, theta double dot is 0. R is 1.6 over square root of 2. R dot equals minus 6.4 over the square root of 2. And R double dot equals minus 25.6 over the square root of 2. And hopefully when we plug things in, everything will come out nice. Okay, now the part I've been dreading, trying to figure out what this looks like when theta is 45, what's happening with this angle of the circle versus the collar. So let me think about that and come back. Okay, so the author was pretty kind to us. It's not that bad, so let me show you. So here's the picture, and when theta is 45, so let me draw that for you. When theta is 45 degrees, so if you start here and you come out at 45 degrees, can you see that it's going to be like that? That the at 45 degrees, if you come out from the diameter at 45 degrees, you'll be right at the top of the circle. So if that's 45 degrees, that will be 45 degrees, and that will be 90 degrees. So that really, really simplifies things. So if you draw the free body diagram when the collar is here, okay, so here's the rod, and there's the collar. So let's redraw that free body diagram. It's much nicer. So right up there, and well, let me even try to draw it. Like, what it would look like. So you've got this collar at 45, and then you've got this collar that's along a circle happens to be right at 90. So the original directions that I wrote, I had them going this way. Okay. The force of the rod, and that's going to be 45 degrees. And then the force on the circle happens to be vertical. the force from the circle on the collar. That's really nice. Okay, so that will equal when we're at 45 degrees. So let me try and draw that again. There's that collar with this extra piece here. Okay, so we're going to have M, a radial, and M, a theta, and everything is at 45 degrees. So you can't go wrong. Everything is 45 degrees. Okay, so we're ready to go. We just have to remember what AR and A theta are, and so we've done this several times now. So the radial acceleration is r double dot minus r theta dot squared, so the acceleration going out minus the centripetal coming in. And we had the theta acceleration, remember, is just the radius times the angular acceleration plus the weird r dot theta dot twice. Okay, so let's put that all in. So that's minus 20, there it is, 25.6 over square root 2 minus r, which was, because r dot was negative, r double dot was negative. R is 1.6 over square root of 2, and theta dot was 4, so theta dot squared 16. Figure that out in a little bit. R is 1.6 over square root of 2. I didn't have to do that because theta double dot 0. Plus 2 times r dot, which is minus 6.4 over square root of 2 times theta dot, which is 4. So let me clean these up a little bit and come right back. So coincidentally, or maybe it was designed like this, both of these come out to minus 51.2 over square root of 2. Okay, so we're ready. We could either take x and y components or r and theta components, and looking at it, 3 out of the 4 things in the free body diagram are in r and theta direction. The normal force of the circle is in the y direction, so what I'm going to do is I'm choosing to do r and theta components because 3 of them are already in those directions. So what that means that I have to figure out is what's the angle of this vertical force relative to 45 degrees, and everything is 45 degrees in this problem, which makes it nice. You couldn't get it wrong. If theta was like 30 degrees, this problem would have been a complete nightmare. Okay, so here we go. I'm going to do, and so if you look at the forces, the rod is in the theta direction, and the circle has a component in the theta and the r direction. So the circle force is the only one that has a component in the r direction. So that tells me it would be easier to do the r direction first because there will be only one unknown. It doesn't really matter if you figured that out, but it just makes it easier. And this is sort of why I can do problems quickly, is you just think ahead like that. Okay, so doing the r direction, you get the force from the circle times cosine 45 degrees, which is 1 over square root 2. And there is no component of the rod force in the r direction, so that's nice. That's why we did it. And so that will equal the mass, which was 0.5 kilograms total, not 0.5 for each collar, making it 1 kilogram, times the radial force, which the radial acceleration, which was minus 51.2 over square root 2. And so that's nice. The root 2's cancel, and we get that the force of the circle onto the collar is 25.6 minus 25.6 newtons. The negative means the opposite of what we assumed, so it's pushing in. Okay, now let's do the theta forces. So some forces in the theta direction will equal ma theta. Okay, so if you look in the theta direction, obviously you have the force of the rod, okay, and you have the force of the circle times cosine 45 degrees. Okay, so plus f circle times cosine 45, which is 1 over root 2, okay, equals ma theta. Again, mass half a kilogram, and a theta happens to be minus 51.2 over square root 2. Okay, so if you put in what the force of the circle was, F rod plus F circle happened to be minus 25.6 over square root of 2 equals half of 51.2 is 25.6. Look at that. And so that means the force of the rod on the collar is 0. I did look at the solution, and that is correct. So let me double check the other one. 25.6 newtons, and that is correct. Okay.